Visiting every node of a graph exactly once refers to graph traversal. As you can see, there are two popularly known graph traversal techniques. Number one is breadth first search or BFS, and the second one is depth first search or DFS. In this video, we will be discussing breadth first search technique. Remember, the BFS or Dfs traversals are not unique. Also, we can start from any vertex. We can choose any vertex as our starting vertex and keep visiting every node of the graph till all the nodes have been covered. Remember, BFS uses a queue data structure to implement its operations, and when you apply BFS on a tree data structure, one of the traversals that you get will be same as level order traversal of the tree. Now, with this background information, let's try to develop an intuition on how to apply BFS on these three graphs. Okay, so I'll show you how to go about things. Now, what you can do is you can choose any vertex as your starting vertex. Let's choose. I'll show you a number of traversal techniques. That means I'll show you a number of BFS traversals for every graph. Let me show you 3 traversals for each of these graphs. And in this way, you will be able to develop an intuition. So see, okay, let me just move this up a bit. Yeah, I think that's better. So here, in the first case, I'll choose my starting node. Let me choose my starting node. Let's call it start to be A. So I'm choosing my starting node to be A. Now let's see how to go about carrying out a BFS traversal. So a start node, which is A, is visited. Okay, let's visit A. Now BFS tells us to visit all the adjacent nodes of A. So which is our current node? Our current node is our starting node, which is A, and we have to visit all its adjacent nodes. So which are the nodes which are adjacent to A? B is adjacent to A because it has a direct connection with A. C is adjacent to A because it has a direct connection. E is adjacent to A, it has a direct connection, and D is adjacent to A because it has a direct connection. These lines are your edges. So you have 4 vertices which are adjacent to vertex A. So they are B, C, D and E. Now you can visit them in any order that you want. That's why in this way you can generate multiple BFS traversals. So let me visit B first, then let me visit C, then I'll visit D, and then I'll visit E. So after visiting all the adjacent vertices of A, I look at the next vertex. That means, which was the first vertex that I visited? Which was the first adjacent vertex of A that I visited? I visited B first. So now my job is to visit all adjacent vertices of B. So I find that the adjacent vertices of B are A, D and E. But in my output list, I can find that B, D and E, they have already been visited. So I will not visit them again. Now, which was the next vertex to be visited after B? The next vertex was C. So now I'll look at all adjacent vertices of C. So you can find that the adjacent vertices of C are A, F and G. Now out of these 3 adjacent vertices of C, A has already been visited, which you can see in your output list. And one more thing is F and G, they have not been visited. So you can visit them in any order that you want. So I'll visit F and then I'll visit G. Now what I find is I have visited all the vertices of my graph. See, how many vertices do you have? You have 4 here and 3 here, 7. So 1, 2, 3, 4, 5, 6, 7. All 7 vertices have been visited. So my BFS traversal is complete. Now let me show you another BFS traversal. Let the start node be A itself. So again, now what I can do is I'll first visit my starting node, which is A. Then I look at all the adjacent vertices. The adjacent vertices are B, C, D and E. I can visit them in any order that I want. So let me just alter the order now. In the previous case, I visited B first, followed by C, followed by D, followed by E. Now what I'll do is let me visit C first. I'll visit C, followed by D, followed by B, followed by E. Now, after visiting the adjacent vertices of A, which vertex will I look at next? I'll look at the vertex C because it was the first vertex which I visited. The first vertex of A, the first adjacent vertex of A which I visited was C. So now I look at all adjacent vertices of C. So what are the adjacent vertices of C? A, F and G. Now A has already been visited, so I'm left with F and G. Now I find that all vertices have been visited, so my BFS traversal is complete. Let me show you another BFS traversal with a different starting node. Let the starting node now be G. So how would I go about it? Now first what I'll do is I'll visit my starting node, which is G. Now I look at all adjacent vertices of G. What are the adjacent vertices of G? C and F, because you have direct edge links with C and F for G. So you will visit them. So you will visit C and then you will visit F. You can also alter the order here. You can visit F first, then you can visit C, so you'll get a different traversal. I'm visiting C first, followed by F. Which is the next vertex that I look at? I'll look at C. So what are the adjacent vertices of C? The adjacent vertices of C are A, F and G. Out of these three, F and G have already been visited, so I'm left with A, so I'll visit A. Now which is the next vertex that I look at? I have looked at G, I have looked at C, now I look at F. So how am I getting this order? You get this order from the queue. Don't worry, I'll show you an implementation where I'll use a queue to show you the steps, that how insertions and your deletions take place from the queue as BFS traversal moves along. For now, let's try to develop the intuition. So with F, now my current vertex will be F. So what are the adjacent vertices of F? C and G. But both C and G have been visited. So I'll move on to the next vertex. The next vertex happens to be A. Now I look at the adjacent vertices of A. What are the adjacent vertices of A? B, D, E and C. Now out of B, D, E and C, C has already been visited, but B, D and E have not been visited. So by visiting these vertices B, D and E, I am able to complete my BFS traversal. So you could have altered this. These three vertices could have been altered to get a different traversal. You could have visited D first, B first, then E, or maybe E followed by B followed by D. So in that way, you get a number of BFS traversals. That's why we say that a BFS traversal is not unique. We'll later on see, not in this video, in the next video, we'll see that even DFS is not unique. Okay, now moving on to this example. Okay, now let's look at example number 2. Like I mentioned that when applied on a tree, one of the traversals, one of the BFS traversals will be same as level order. I'll show you that here. So in my first case, I'll assume my starting node to be 27. So if my starting node is 27, what will I do? If my starting node is 27, I'll first visit the adjacent vertices of 27. What are the adjacent vertices? 12 and 30. Okay, so let me visit. So I'll first visit my starting node, which is 27, followed by its adjacent vertices, 12 and 30. So I'll visit 12 and then I'll visit 30. Now, looking at 12. Now, which is the next vertex I'll look at? I'll look at 12. Now, 12, the adjacent vertices of 12 are 8 and 9. So I'll visit 8 followed by 9. Next, I'll look at the adjacent vertices of 30. What are the adjacent vertices of 30? 50 and 40. So I'll visit them. 50 followed by 40. Now, if you observe, if this order that you got, this BFS traversal that you got, is same as the level order traversal. So first you would visit the nodes present at level 0, that is 27, followed by 12 and 30, followed by 8, 9, 50 and 40. And that is exactly what I've done here. So this proves this statement that when applied on a tree, BFS is same as level order. One of the BFS traversals is same as level order. Okay, now let me show you another BFS traversal on this same tree. Remember, a tree is also a graph, an acyclic graph, right? A tree will not contain any cycles, whereas a graph may contain cycles. Now, what you find is the starting vertex to be, let's say the starting vertex is 40. So I'll visit the starting vertex first, and then I'll visit the adjacent vertices of 40. So what are the adjacent vertices of 40? Only 30. So let me visit 30. Now, after visiting all adjacent vertices of 40, I'll move on to the next vertex. So which is the next vertex that I have? 30. Now, what are the adjacent vertices of 30? 50, because it has a direct edge, 40 and 27. So out of 40, 50 and 27, 40 has already been visited. We are left with 50 and 27. We can visit them in any order. So let me visit 50 first, followed by 27. Now I'll move on to the next vertex. Which is the next vertex? 50. So let me see what are the adjacent vertices of 50. I find that 50 has only one adjacent vertex, which is 30, but 30 has already been visited. So I have nothing to do with 50, nothing left. Now I'll move on to the next one, which is 27. Now what are the adjacent vertices of 27? 12 and 30. Out of 12 and 30, 30 has already been visited. We are left with 12. So we will visit 12. Now after visiting 12, we find that the adjacent vertices of 12 are 8 and 9. So we can visit them. So let us visit 8 followed by 9. So this is one more Bfs traversal that you get with the starting node as 40. Now these two examples that we saw here, these were for undirected graphs. Now let's look at example 3 where we have a directed graph. Remember, your graph traversal techniques Bfs and Dfs can be applied on both directed as well as undirected graphs. So let's apply the Bfs on this graph. Okay, again it all depends on the vertex you're starting with. So let me start off with a vertex of, so let my starting vertex be 1. Let my starting vertex be 1. Now I look at the adjacent vertices. What are the adjacent vertices of 1? Where you have outgoing edges from 1 to those vertices, you will be calling them adjacent vertices. So from your current vertex, which is 1, wherever you get outgoing edges to vertices, you will consider those vertices to be your adjacent vertices. So the first thing that you do is you visit the current vertex, which is your starting vertex 1. Then you look at its adjacent vertices. What are the adjacent vertices? 2 and 6. So you visit them. You can visit them in any order that you like. I'll visit 2 first, followed by 6. Now look at the next vertex that you have to encounter. The next vertex is 2. Now look at the adjacent vertices of 2. The adjacent vertices of 2 are, if you observe, only 3. See, 1 is no longer an adjacent vertex. Why? Because there is no outgoing edge. There is an incoming edge. This is an incoming edge. The one that you see here from 1 to 2. This is an incoming edge. For a vertex to be adjacent to 2, there has to be an outgoing edge from 2 to that vertex. I'll repeat this point. For a vertex to be adjacent to my current vertex 2, there has to be an outgoing edge from vertex 2 to that vertex. So from 2 to 3, there is an outgoing edge. So I'll visit 3. I'll visit 3. Now next vertex that I should consider is 6. But I find that 6 has no adjacent vertex. See, there are no outgoing edges from 6. That's why there are no adjacent vertices of 6. Now the next vertex to consider is 3. Now 3 has exactly one adjacent vertex, which is 4, because there is an outgoing edge from 3 to 4. So we'll visit 4. Now the next vertex to consider is 4. Now I can see that there is exactly one outgoing edge from 4 towards 5. So I'll visit the adjacent vertex of 4, which is 5. So let me visit 5. Now the next vertex that I should consider is 5. And 5 has 2 adjacent vertices. See, there is an edge going back from 5 to 2, and there is an edge from 5 to 1. So there are 2 adjacent vertices of 5, 2 and 1. But we can see that 1 and 2 have already been visited. So we'll not consider them again. So this is our Bfs. This is a breadth first search traversal on this graph. Let's try one more. Let's try one more example. So let me take my starting vertex as 5 this time. So again, I'll visit 5 first. Now what are the adjacent vertices of 5? The adjacent vertices of 5 are 2 and 1. So I can visit them in any order. So let me visit 2 first, and then I'll visit 1. Now the next vertex that I should consider is 2. So I'll consider 2. I'll consider its adjacent vertices. There is exactly one adjacent vertex of 2, which is 3. So I'll visit it. Then I'll consider 1. Now from 1, I have 2 adjacent vertices, 2 and 6. 2 has already been visited. I'll consider 6 and I'll visit it. Next is 3. Now from 3, there is exactly one adjacent vertex, which is 4. So I'll visit it. Next vertex to consider is 6. From 6, there are no adjacent vertices, so I have nothing to do. I'll consider the next vertex, which is 4. From 4, there is exactly one adjacent vertex, which is 5, but 5 has already been visited. So this is our Bfs traversal. Okay, so I hope you have understood these examples. What I'll do is, now I'll take up a different type of question that you may be asked in examinations. So let's see. Okay, now this question that you see, this has been asked in GATE 2008, and the next one has been asked in GATE 2017. And I got this question from examination portal, which I found to be a bit challenging. So we'll see how to go about things. Now here, the question is a bit different. In the previous cases, if you saw, in these three examples, what we did was we listed out various Dfs traversals on different graphs. Now, the question is a bit more restrictive. You have been given a graph and you are being said that Bfs has been implemented using Q data structure. That is understood. Bfs is always implemented using Q. Now, one possible order of visiting the nodes of the following graph. That means given this graph, out of these four options, which one represents a possible Bfs traversal on this graph? Given this graph, out of these four options, which one represents a possible Bfs traversal on this graph itself? So what we'll do, we'll check every option and see which one is correct. So let's start. Let's consider one option at a time. So we'll start with option A. I'll just change the color of the ink. I'll switch to blue so that you can understand better. Now here, let's start with the first option. Now the first option here is M. So that means the first node that is visited, this may or may not be a Bfs. This may or may not be a Bfs traversal on this graph. We'll have to check that. So we can see that the first node that is shown here is M. That means M must be my starting vertex. Okay. So from M, what are the adjacent vertices? R, Q, and N. So the next node following M can be any one of these three. See, since the adjacent vertices of M are N, Q, and R, in the Bfs traversal, the node following M can be any one of these three. So the node following M is N, which is allowed because N is adjacent to M. So this is fine. So up to this point, it's okay. Now what we'll do is, we will see the next node. Now the next node should be, see, in Bfs, I have to consider one node at a time. So I'm considering M now, and I have to visit the current node, which is M, which I've done, and I have to visit all the adjacent nodes of my current node. That means I have to visit all the adjacent nodes of M. That means N, Q, and R. See, there is a direct link with N, there is a direct edge with Q, there is a direct link with R. So since there are direct links with these three vertices, I'll have to visit these three vertices in any order. Not necessary that I have to follow a particular order. I can visit the adjacent vertices of my current node, which is M, in any order. But I can see that after N, instead of visiting R or Q, the answer that has been given, the option that has been given is O, which is not correct. So I have to discard this option because M should be followed by N, Q, and R in any order. Okay, now let's consider option B. Now in option B, they have changed the starting vertex. The starting vertex now is N. Now if N is my starting vertex, I'll visit it first, which they have done. Then I have to visit M, O, and Q. M, O, and Q are the adjacent vertices of N. If you observe, there is a direct link between N and M, N and O, N and Q. So I'll have to visit these three vertices in any order. So after N, I can see that I'm getting Q. So this is fine. Then I'm getting M. So that is also fine because M is also adjacent to N. And then I'm getting P. Then I'm getting P. But you can see that there is no direct link. There is no direct edge between N and P. That means this is incorrect. Following Q and M, I should have visited this node. I should have visited O, but I'm visiting P. So N, I'm visiting N, then I have to visit all adjacent vertices of N. They are M, O, and Q. But after visiting Q and M, I am visiting P instead of O. That's why this option has to be rejected. Now next, if I start off with Q, then I find that the adjacent vertices of Q are M, N, and P. So I have to visit M, N, and P in any order. So that is what I've done. See, I visited Q, then I visited M, N, P. Next, I have to consider M. So I have to consider the adjacent vertices of M. So what are the adjacent vertices of M? N, R, and Q. N has already been visited. So I'll have to visit R and Q in any order. So I can find that after visiting M, N, and P, I'm visiting R. So that is fine. And also remember, since Q has been visited, I'll not be visiting it again. If you observe that, See, I am visiting all the adjacent vertices of Q. They are M, N and P. The next vertex to consider is M. The adjacent vertices of M are N, Q and R. Out of these three, N and Q, N and Q have already been visited. So I'll not be visiting them again. So the only adjacent vertex of M that I have to visit is R. That is what I've done. Now I'm left with only O. The next vertex that I'll consider is N. What are the adjacent vertices of N? Q, M and O. Out of Q, M and O, I can find that Q has been visited. M has been visited as well. See, M has been visited as well. And I'm left with O. So I'll visit O. So this is the correct option. We'll not restrict ourselves to 3 options. We'll visit this one as well. We'll explore this. Let's see if this turns out to be correct or not. And even if it's incorrect, how or at which point does it become invalid? So we are starting off with Q because it's my first vertex. So now I'll consider the adjacent vertices of Q. They are M, N and P. So I'll have to visit M, N and P in any order. So I'm doing that. I'm visiting M, N, P in any order. The next vertex that I'll consider is M. So the adjacent vertices of M are R, Q and N. Out of R, Q and N, I can find that Q and N have already been visited. So my next job is to visit R. But see, instead of visiting R, I am visiting O. So that's why this becomes incorrect. So had this option been correct, then I would have had to write Q. I'm starting off with Q. So I'm visiting its adjacent vertices M, N and P. I'm done with that. And then I'll consider M as my next vertex and I'll visit its adjacent vertices. But out of the adjacent vertices of M, I find that N and Q have already been visited. I'm left with R, so I have to visit R. Next, I'll have to start off with N. N is my next vertex. Now, out of the adjacent vertices of N, which are Q, M and O, I find that Q and M have already been visited. I'm left with O, so I'll visit O. And this happens to be exactly same as my correct option. So this is how you would solve such a question. Now, moving on to the next one. It's the same thing. The statement is the same. This is the statement that was given for this graph as well. We have to find the correct option. So again, let's examine each option one after the other. So I can find that, okay, I think I've made a slight mistake. Have I? No, I think I'm good. I'm good to go. Yeah. So my starting vertex is M. My starting vertex is M. So I'm at M. Now I'll visit M and I'll visit the adjacent vertices of M. What are the adjacent vertices of M? N, Q and R. So N, Q and R are the adjacent vertices. So I'll visit them in any order. But I find that I'm visiting N, then I'm ending up visiting O. But O is not an adjacent vertex of M. So this option is rejected. Next, examining option B. I'll start off with Q. So if I start off with Q, I find that the adjacent vertices of Q are M, N, O and P. Q is visited. Then I'll have to visit M, N, O and P in the same order. So I'm visiting M. So I'll visit M, N, O and P in any order. So I'll visit M, then I'll visit N, then I'll visit O and P. But I'm ending up visiting R. And R is not an adjacent vertex of Q. See, there is no direct connection between Q and R. So R is not an adjacent vertex of Q. So that's why this option is rejected. Now let's examine the third option. The third option is you're starting off with N. Starting off with N, what are the adjacent vertices of N? M, O and Q. So I'll visit N, then I'll visit M, O and Q in any order. So I'll visit Q, I'll visit M, but I'm ending up visiting P. But P is not an adjacent vertex of N. See, there is no direct link between N and P. So I cannot say that P is an adjacent vertex of N. So instead of visiting all the adjacent vertices of N, which are M, O and Q in any order, I am ending up visiting a non-adjacent vertex. That's why this option is rejected. So I'm left with this one. Obviously, this has to be correct. But let's just verify. Let's just verify our claim. So we are starting off with P. So P is my starting vertex. So I'll visit it. I'll visit the starting vertex. And now I'll visit all the adjacent vertices of P. What are the adjacent vertices of P? O and Q. So I'll visit them in any order. That's what I've done. I visited O. I visited Q. Next vertex to consider is O. Now starting off with O, how many adjacent vertices do I have? N, Q and P. Out of N, Q and P, I find that P and Q have already been visited. Now, the only vertex which is not visited and is an adjacent vertex of O. See, adjacent vertices of O are N, Q and P. Out of these three, Q and P have already been visited. N has not been visited, so I'll visit it. That is what I've done here. That is what they have given in this option. Now, the next vertex to consider is Q. Now, what are the adjacent vertices of Q? The adjacent vertices of Q are M, N, O and P. So, out of M, N, O and P, I find that N has been visited, O has been visited, P has been visited. The only vertex that is left to be visited is M. So, we'll visit it. Next vertex to consider is N. Now, N, what are the adjacent vertices of N? M, O and Q. Out of M, O and Q, I find that M has been visited, O has been visited, Q has been visited. So, all the adjacent vertices of all the adjacent vertices of N have been visited. Now, the next vertex to consider is M. Now, the adjacent vertices of M are N, R and Q. So, out of N, R and Q, I find that N has been visited, Q has been visited, only R has not been visited. So I need to visit it, and that is what I've done here. I visited R, and this happens to be indeed the correct option. Now, let's solve this one. So they're saying that with A as a source vertex, I have to find a Bfs traversal. Okay. So with A, so I can find any Bfs traversal, right? Any Bfs traversal will do. So I'll start with A. So I'll visit it. What are the adjacent vertices of A? B is an adjacent vertex, C is an adjacent vertex, D is an adjacent vertex. So I'll visit all of them in any order that I like. So I'll visit them in this order, B, C and D. Now the next vertex that I'll consider is B. I'll consider B and look at its adjacent vertices. The adjacent vertices of B which are not visited happens to be only E, because A, although being an adjacent vertex of B, has already been visited. So I am left with E. So I'll visit E. Now the next vertex to consider is C. Now I'll consider C. And what are the adjacent vertices of C? E, A and F. But out of E, A and F, E and A have already been visited. I'm left with F, so I'll visit it. Now the next vertex to consider is D. Now starting from D, what are the adjacent vertices? A and F. A and F are the adjacent vertices of D. So I can visit them in any order that I want. But what happens to be the case here is A has already been visited and F has already been visited. So I have nothing else to do with D. Now I'll consider E. Now with E as my current vertex, F has already been visited. Now with E as my current vertex, I find that there are three adjacent vertices, C, B and H. Out of C, B and H, only H has not been visited. So I'll visit H. Now after visiting H, I'll consider the next vertex, which is F. What are the adjacent vertices of F? C, D, H and I. Out of C, D, H and I, only I has not been visited. So I'll visit I. Now I'll consider H as my current vertex. And I find that the adjacent vertices of H are E, F and G. Out of E, F and G, only G has not been visited. So I'll visit G. And I find that 1, 2, 3, 4, 5, 6, 7, 8, 9. All 9 vertices have been visited. If you count the number of vertices here, you'll find 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. So I've visited all the 9 vertices. So I can say that my Bfs traversal is done. So this is one of the traversals, okay? We have been asked to find only one Bfs traversal, and that is exactly what we have done here. Now what we'll do is, we'll take up a concrete example where I'll show you how a queue is used to implement Bfs. After taking up so many examples, I guess you have developed an intuition on how to go about solving Bfs traversals very quickly. Now, if you're asked a long question where you have to show every step, it is important to show the contents of the queue and the visited array every time. So I'll do that right now. So let's see how to go about it. Now, we have been given this graph and we have been asked to find a Bfs traversal. So for finding the Bfs traversal, what you need to do is, you need to first choose a starting vertex. So let's say my starting vertex, I choose my starting vertex to be 1. Okay, I'll choose a different colored pen. Let me choose a black colored pen so it will be easier for you to understand. So my starting vertex is 1. Now at every step, so this is my step 1. At every step, I'll be maintaining a queue. I'll be maintaining a queue data structure. This is my queue. And I'll be maintaining a visited array. So if you're asked a long question, you'll have to show the contents of these two data structures. You'll have to show your queue and you'll have to show your visited array. Now visited array will have an entry for every vertex. How many vertices are there? 8. So there will be 8 entries. So 1, 2, 3, 4, 5, 6, 7, 8. So I'll just label every entry with the vertex value so that it's easier for you to understand. Okay. Now, the first thing that you do is you take your starting vertex. Which is your starting vertex? Your starting vertex is 1. And you perform an enqueue operation. So if you perform an enqueue operation, this is the initial step. So you perform an enqueue operation on your starting vertex. So you insert it in the queue, and let's say this is my output. Okay, maybe I'll show the output here, or no, I think, I think this would be a good place. So whenever you enqueue, this is the initial step, your starting vertex, you also visit it. And when you visit it, you keep a marker here to denote that this vertex has already been visited. So you keep a marker which denotes that vertex 1 has been visited. Now you look at the adjacent vertices. So how will you look at the adjacent vertices? What you will do is, now what I'm about to show you is the repeating step. So now you will perform a dequeue operation. So you perform a dequeue operation and 1 is taken out from your queue. Now after you take out 1 from your queue, what you do is now what is the element that you have? Let's say in item. So item contains the dequeue element. The element which you just dequeued is stored in item. Now you look at all adjacent nodes of item. Which are the adjacent nodes of your item? So how would you do this programmatically? Programmatically, you can find the adjacent vertices of a given vertex using an adjacency matrix. If you represent this graph in your computer using an adjacency matrix or an adjacency list, using that data structure, you can find the adjacent vertices of a given node. So using that data structure, you are able to find the adjacent vertices of this node 1. So here I am doing it graphically. I am not showing you the adjacency matrix or adjacency list separately. If you are implementing a program, you can do that. So from the graph, I can find that 2 and 3 are the adjacent vertices of 1. So what will I do? I'll do 3 things. The first thing that I'll do is I will enqueue them. I'll enqueue 2 and 3. Now the order in which I enqueue will determine the order of my Bfs traversal. So it's not necessary for you to follow any particular order for the enqueue operation. You could have enqueued 3 first followed by 2, or you could have just followed what I've done here. Now that is the first thing that you do. You enqueue. Okay, so this is step number 2. I'm showing you one queue. I expect you to show every step separately. Okay, so step number 2 is when you enqueue 2 and 3, and then what you do? You visit them. So you mark them as visited and you display them in the output. Okay, so I'll show step number 3 separately. So in step number 3, what I have is, I have my queue, which now contains 2 and 3, and I have my visited array. I have my visited array with 8 entries. So that's 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Yeah. So I'll label them. So far, 1, 2, and 3 have already been visited. So I'll mark them as visited with a value of 1. Next, what I'll do is I'll perform a dequeue operation. So if I perform a dequeue operation, we know that queue follows a first in first out algorithm. So the element which was inserted first will go out first. So 2 was inserted before 3, so it will be taken out before 3. So now item contains 2. Now item contains 2. So what happens is, now you look at this node's adjacent vertices. So what are the adjacent vertices of 2? The adjacent vertices of 2 are 1, 4 and 5. So what are the adjacent vertices? Let's say you have a variable called w. In that you are storing the adjacent vertices of the current node. So 4, 5 and 1. These are the adjacent vertices. Now, you take each of this adjacent vertex and you check in the visited array. So you check whether 4 has been visited or not. No, 4 has not been visited. Then you check whether 5 has been visited or not. No, it has not been visited. You check whether 1 has been visited or not. Yes, 1 has been visited. So the nodes which have not been visited, what you do is you enqueue them in any order that you want. So I'll enqueue 4 followed by 5, and the order in which you enqueued them, you show them in the output. So you show 4 and then you show 5. And also you mark the visited array for these two vertices as visited. Next, step number 4. Let's see step number 4. So in step number 4, what I'll do is I'll show step number 4 here itself due to lack of space. So in step number 4, I'll perform another dequeue operation. So if I perform a dequeue operation, the element which was present at the beginning of the queue is 3. So item now becomes 3. So this is my current node to examine. Now, let's say in W, I'm storing all the adjacent vertices of the current node. So what are the adjacent vertices of 3? See, 1, 6 and 7 are the adjacent vertices of 3. So the adjacent vertices are 1, 6 and 7. Now out of 1, 6 and 7, I find that 1 has already been visited, but 6 and 7 have not been visited. So what will I do? I will enqueue 6 and 7 in my queue data structure, and I'll output them in the same order. I'll output them in the order in which I enqueued, and I'll also mark them as visited in my visited array. Right? Next, I'll perform step number 5. I'll perform a dequeue operation, so 4 will come out. Now, my current node is 4, which is denoted by item here. Now, I'll consider the adjacent vertices of 4. So, what are the adjacent vertices of 4? I can find that the adjacent vertices of 4 are 2 and 8. Okay. So, I'll consider the adjacent vertices of 4 to be 2 and 8. Now, I find in my visited array, 2 has already been visited, but 8 has not been visited. So, if 8 has not been visited, what should I do? I should firstly enqueue it. I'll enqueue 8, I'll mark it as visited, and then also output 8, right? Now, we can see that the visited array has been completely filled up. That means all my nodes have been visited. All my nodes have been successfully visited. So, we might stop the procedure here, but if you're writing a program, your stopping condition will be till the time the queue is empty. Is the queue empty? No, the queue is not empty. So, I'll show you the repeating steps till the program will terminate. So you will now enqueue 5. So this will be step number 6. In step number 6, you have enqueued 5. So your current item is 5. Now you look at the adjacent vertices of 5. The adjacent vertices of 5 are 2 and 8. Now you look at the visited array. In the visited array, you find that 2 and 8 have already been visited. So there's nothing left to be done. So there's nothing left to be done with 2 and 8. So you move on. So your current so with 2 and 8, it's done. And next what you do is, you consider 6 to be your current vertex. So if 6 is your current vertex, this will be your step number 7. So if 6 is your current vertex, what are the adjacent vertices of 6? 3 and 8. You look at the visited array, both 3 and 8 have been visited. So there is nothing left to be done. Next you will enqueue 7. So 7 is your current vertex or current node. In fact, it's 7, not 8. I'm sorry about that. So 7 is your current node. Now you look at the adjacent vertices of 7. The adjacent vertices of 7 are 8 and 3. Now in the visited array, you find that 3 and 8 both have been visited already. So since they have been visited already, what you do is you ignore it and then you perform an enqueue operation again. You perform a dequeue operation. You perform a dequeue operation and you get 8 as your current item. Now you find that the adjacent vertices of 8 are 4, 5, 6 and 7. But all of them have already been visited. So there's nothing that you need to do. And finally, your queue is now empty and you can stop the procedure and conclude that your BFS is 1, 2, 3, 4, 5, 6, 7, 8. So this is how you would show every step in your examination when you are asked a long question on BFS. So I hope you have been able to develop an intuition as well as understood how a queue is used to implement the BFS algorithm. If you have any questions or if you have any suggestions, please feel free to comment in the section given below. I'll see you in the next video where I'll be discussing depth first search. Thank you.